Design of full adder using multiplexer. Already we studied what is multiplexer and how to implement logic gates using multiplexer. Now full adder. Full adder is a digital circuit which adds 3 bits. If you consider the example, out of the 3 bits, 2 bits are from the single bit number A and B, and the last bit is carry generated from the previous stage. Full adder adds these 3 bits and it generates the output in the form of sum and carry out. We can represent this behavior in the form of truth table. In the truth table there are 3 input variables A, B, C named over here. Output is sum and carry out. 3 input variables and different total 8 combinations. For each input combination, what is respective output is mentioned in the truth table. Before implementation of any combinational circuit using multiplexer, we have to consider few points. That is, which method we are going to use for implementation, what would be the size of the multiplexer, and how many multiplexers are required. All these things will be clear if you know the truth table of that particular combinational circuit. Here we are going to use a direct method for implementation, which is the simplest method. Now selection of multiplexer, that is what would be the size of the multiplexer. There is a formula 2 raised to number of input variables of the full adder, as here combinational circuit is full adder. It is equal to required number of inputs of multiplexer. In this case, 2 raised to number of input variables of full adder, it is 3. So 2 raised to 3, we will get 8. Hence we needed a multiplexer with 8 input. So here we needed 8 as to 1 multiplexer. So the size of the multiplexer now, it is 8 as to 1. Next is how many multiplexers we required. In this case, we have 2 output variables, just sum and carry out. So number of output variables for that combinational circuit, here output variables for the full adder, is equal to number of multiplexers required. So as we have 2 output variables, we need here 2 8 as to 1 multiplexer. 1 multiplexer is going to give us sum output, another multiplexer is going to give us carry output. So here the table is rearranged, truth table of the multiplexer is rearranged. Multiplexer 2, it is giving us sum. So multiplexer 2, here multiplexers. This is considered multiplexer 2, which is giving us sum. And now how the inputs of the full adder is connected. A, B, C inputs of the full adder is connected to the select lines of the multiplexer. And according to the truth table requirement of the output, we have connected the inputs of this multiplexer to either logic 0 or to logic 1. See here, we consider one case. Suppose for 3, combination 3, consider here. In this case, when there is a value 0, B value 1 and C third input is 1, we expect output sum should be 0. According to the behavior of the multiplexer, when at the select line there is a 0, 1, 1 combination, actually third input, what you applied at the third input, either logic 0 or logic 1, is getting appeared at the output as it is. As we want output 0, logic 0 at the sum, of course we need to apply or we need to connect this input number 3 to logic 0 so that we will get logic 0 at the output over here. So see here, you can observe it in this slide that for sum, as we have taken that previous example, we consider we have taken here 0, here 1 and here 1 at the select line. So if it is 0, 1, 1, what happens? This 3 is transferred. What you applied at the third input is transferred at the output sum. As per the truth table, we expect over here 0. So if you want 0 at the output of this multiplexer, you have to apply 0 at this input. Hence, this third input is grounded. Okay. Likewise, we have to go for all respective connection. Where we want some value 1, at that time, where there would be some value 1, if I consider 0, 0 and 1 input. So 0 plus 1, output sum will be 1, and according to multiplexer behavior, 0, 0, 1 means input number 1 is whatever you apply over here is getting transferred over here. As we want at this combination 1, we have to apply over here logic 1. Okay. Then if you consider next is for carry out. Same combination, if I consider 0, 1, 1, we expect multiplexer which is producing carry out, it should provide you 1. So what should we connect to the third input of that multiplexer? As I want output 1, I have to connect third input of the multiplexer to logic 1. Okay, so in this figure you come to know, if I apply over here as we previously applied that considered example 0, 1, 1, and I want over here 1, as per the behavior of multiplexer, actually third input what you applied over here is getting transferred at the output when select line combination is 0, 1, 1. As I want 1 at the output, I must have to apply logic 1 at this input. Hence, this third input is connected to VCC. This way, it is very easy to implement any combinational circuit using multiplexer by direct method. Just see this truth table, apply this select line, apply this input variables or consider this, attach it to the select lines. Whatever be the required output corresponding to that corresponding multiplexer input, you have to apply that particular logic. So logic 0, multiplexer input 0 is connected to logic 0 for sum. Multiplexer input 1 is connected to logic 1 for the combination 0, 0, 1. So this is by deciding this. Here min-term list is given at logic input 1 to at the multiplexer input 1 to 4, 7. We expect sum output 1. So these 4 inputs are connected to VCC, rest are connected to ground. And for Cout, these 4 inputs are connected to VCC, rest are connected to ground. Same method and the same procedure you can apply for this problem. Students has to solve now these two problems by the same method. Think on it. 3-bit odd parity generator you have to implement. And second problem is 3-bit binary to gray code converter. Follow the same procedure. Okay.